So I'm going to talk and then I'm going to pause and then I'm going to turn it back on because I've done this lesson before and my voice didn't show up for 10 minutes. So yeah, frustration. There, that should work. Okay, so this is vectors. You're here. And vectors should remind you of physics if you've taken physics. Calculus also has some physics components to it as well, but vectors very much so, especially if you're going into engineering. So the first thing I'll do is I'll share this first slide with you after I put it on big screen so you can actually see what we're talking about. Page width. So use for vectors, and I don't know much about any of these things. I can do the math. So because I don't teach physics and because I haven't studied physics, I can't tell you exactly the places where you model problems in physics all through it. I know that there are some. I know we touch on some. I don't know anything about fluid flow theory, but I can imagine it uses vectors just based on the name. Economics, I have taken one economics course in my life, so I don't know where it fits in, but I know when I Googled to give you places where vectors happens, this is one of them. And believe it or not, there is some vectors in psychology. Definitions. So if you've taken advanced functions or looked at any of my videos for that, you might have seen scalars and vectors before, especially if you have taken physics. So scalars are quantities that have magnitude only. That means you only need, you only need a number. You do need units, but you don't need any direction. So examples of that are age, mass, speed, and distance. And we come back to a couple of these in a second when I go to talk about vectors, which are slightly different in that they have magnitude, so they have a number with units, and they have a direction. So you have to specify a direction. So examples of that, especially if you've looked at physics before, force, acceleration, and here's where we come back to speed and distance. Velocity is speed with a direction. So velocity is a vector's quantity, and speed is a scalar quantity. Displacement is distance in a direction. So distance is a scalar quantity, displacement is a vector quantity. So you have to be more specific with vectors because you have to name a direction. When we represent vectors on paper, we do so with a directed line segment. That means you have to direct it, which is why it's in italics here. A directed line segment means you need a point to start with. It does not have to be a big dot like this. It can just be a starting spot. But you have to have an arrow on the other end to say, this is going in this specific direction. So it's an arrow from one point to another point. So it's not a line segment, it's a directed line segment. The initial point, the starting point, is also called the tail, and the terminal point, the ending point, is called the tip. And it matters how you talk about vectors. So for this particular vector, this is BA, because it starts at B and it goes to A. So it says since the direction is from B to A, this is vector BA. And you cannot write BA like that. That is BA, the line segment. If you mean B to A with a vector, you need to have either a full scale arrow on the top. I have a habit of doing a half arrow on the top. Still, you have to specify that it's a vector, and that's how you do it. Another way to specify a vector, other than going from capital letter to capital letter, is to have some sort of lowercase letter also with the vector symbol hanging over that lowercase letter. And it says here, BA is a line segment, as I've said, without the hat on it, not a vector. So you have to be very, very specific when you're writing stuff down, and you can't get lazy, otherwise you mean something totally different, and that something different is incorrect. So as I said, it's also possible to use a lowercase letter for a vector, example M with an arrow on top, M is super popular. We'll see why later. If I ask you for the magnitude or length of a vector, there is a symbol for that, and that is taking whatever the vector is, whether it's M with the arrowhead on top, or vector BA, which is how you read this, vector M, you put the absolute value signs on them, meaning you put bars on either side, and what that does is it tells you to find the magnitude or the length of that vector, and we will get more into that as well. All right, so next slide. This is a very informational based note. So there are some rules, and in a sense, rules are made to be broken, so we don't do this all the time when actually we should do our best job possible, especially if you are going into some sort of field where accuracy is important. Building bridges, building homes, building anything that you don't want people to be hurt in. If you are flying a plane, you want to make sure that your vectors follow this rule. When representing a vector by a directed line segment, the length and direction of the line segment must depict the actual magnitude and direction of the vector quantity. So you have to do a really good job of scale drawing, is what that says. So an example is a wind of 50 kilometers per hour in a northerly direction could be represented by a 5 centimeter line pointing up. So here's your little compass rose telling you where north, south, east, west is. And up is north, typically. So I've drawn a vector P to Q, represented with a capital P, then a capital Q with the vector hat on it. And I've represented that, and I've said, okay, and you can't tell in this picture, but this is a 5 centimeter line, and it is pointing up. So that means 1 centimeter represents every 10 kilometers per hour. So that is what we mean by a scale drawing in vectors. It is important that your directed line segments, even though in the future of these notes I won't always do that to map out vectors, your directed line segments should be using rulers. So they are line segments. They aren't freehand segments. Okay. Some definitions. Equal vectors. Equal vectors have the same magnitude, so they have the same length, and they have the same direction, as opposed to opposite vectors, which have the same magnitude, so they have the same length, but they go in opposite directions. So the example here is actually an opposite vectors example. So I've got an XY vector. That means this is capital X, this is capital Y, because I've said X to Y. And this apparently is PQ, so this is P and this is Q, because we're going in that direction. And if you notice, the arrowhead for PQ is here. So this one has a downward slant, and this one is going in the opposite direction. That means that PQ is equal to negative XY. So what matters is that XY and PQ are parallel. That means they're going in the same direction. That means that they're acting like railroad tracks, which are going in the same direction. So they don't have to go, they don't have to overlap each other. I don't know what I did here. I did lock it in. So you don't have to have this happening. They don't have to be like literally lying on top of each other as long as you've drawn them parallel. And PQ is also known as negative XY. We'll deal with this later on in some notes as well. There is something called the zero vector, and the zero vector has zero magnitude. And the direction is undefined because if you are going nowhere, your direction is an unknown. What is important is that you realize that I have pretty bad notation in my note in that I have a little dash here. That is not a negative zero, that is a zero. So these are little points, so bullets. And the zero vector is not represented by a zero. It is represented by a zero with the vector symbol on top. So that is, again, pretty important to communicate things properly in ways that everybody will understand. All right, last slide. So the question is, are the following vectors equal? Explain your reasoning. So, take a look at that. Pause if you want. And it'll give you the answer in a second. So the answers to these questions without reasoning, and I'll come back and do reasoning in a second. The answers for this is no, these vectors are not equal. Yes, these vectors are equal. No. So let's go over the explain your reasoning business. So these are vectors, they're directed line segments, and I've told you they're exactly the same length, so they have the same magnitude. So they do have the same magnitude here, which is a good thing, but that's only half the battle when you're talking about vectors. They have opposite directions. And because they're opposite directions, this set right here, are opposite vectors. This one, directed line segments, they are parallel from what we can tell. So yes, this has the same magnitude and direction. And we'll see if I can spell direction neater this time. There, much better. And the tricky one on here is this one. I'm going to think that some people are guessing yes for this, but the truth is this is a no, because even if these are exactly the same length, so let's say they are the same length, even though there's no indication on the lines that they are the same length, they're line segments, these aren't vectors because the arrowheads aren't at the end. I hope you remember back to your grade 9 days where this means parallel lines. These are parallel lines, but they're not vectors. Actually, they're parallel line segments because they stop. They are not vectors. If they were vectors, the arrowhead would be at the end saying this is the terminal point or the tip of the vector. So until they have that, they're not even vectors, so which is why I get to say nope. These are not equal vectors. All right, last question. Name all sets of equal vectors in the given parallelogram. So what we're going to do is we're going to name equal vectors, just like the question says, but I do want you to know that there are vectors here that you can't see, and by that I mean, and I'm going to do this without a ruler, even though that's bad, there is a vector B to D, there is a vector D to B, there is a vector A to C, there is a vector C to A. So there's vectors all over the place, including the ones that you may actually be able to see here. Now, having said that, this is very similar to the last question. I think that's what's under this box. Notice, this is the same situation as 1C above. So this is showing you parallel lines, or line segments, because it's a parallelogram. That makes A to D, so that makes this line segment and this line segment the same length as each other. It makes this one the same length as this one. So the reason you get to call these vectors as opposed to this is that this one didn't have letters on the end or even letters, lowercase letters on the vectors, so you couldn't actually name them. These ones we can make vectors, meaning we can state them. So I'm going to draw on it and erase. But there is a vector, make sure you use the vector hat, A to D. And it is exactly the same. So it is an equal vector to B to C. Now, just to be a little bit crafty, there is also a vector D to A, and it is exactly the same as C to B. So those are equal vectors. Now let's work on the sides rather than the tops and the bottoms. B to A vector is the same, equal vectors, to C to D. And going in the opposite direction, A to B equals D to C. And those are the equal vectors in this particular parallelogram. So, there is a handout if you're following along with this actual course. Let's see if I've got this. Actually, I'm going to pause it and come back with the Google site. Okay, here's the Google site. So what I'm doing is I am doing the note. In this case, it's an attached sheet. Here's the sheet. There is a note. There will be this video when I'm done. And there is a blank note. So if you open up any of these little blank notes, come on, do it. It is the exact same note as I deal with, only you have all the pictures drawn for you, which might help. So in the case of these ones, there are your vectors, there's the parallelogram. So just so you know, that's all set out for you, and I have great plans to do that all the way along. So as you can see, when we get to the second note, there's a blank note and the video. Textbook work, blank note, video. Videos have not been linked yet. And I do that all the way along because it's a bit annoying to try to draw the pictures that I've got to match on your page. So that's there for you if it helps. Anyhow, enough about me. I'll be back with the fourth one because I did 2 and 3 last night when my mic was actually working. Bye.